Welcome to the Natural Reward Podcast. I'm your host, Owen Gilbert. I'm very excited today to have Nikunj Goel as my guest. Nikunj received his BS in Physics and Environmental Sciences at the Indian Institute of Science, where he was advised by Vishu Guttal. He received his MS in Ecology and Evolutionary Biology at Yale University, where he's advised by Stephen Stearns. And he received his PhD in Ecology, Evolution, and Behavior at the University of Texas at Austin, where he was advised by Tim Keitt. Nikunj is doing some interesting work on theoretical ecology and spatial sorting. Nikunj, what first got you interested in biology?
This is something that I really like to talk about, because my entry into biology was more like because of a series of unexpected events, I would say. I guess like when I was in my 8th standard, I really didn't like biology, and I think so that was partly because, also that when I was in my 8th standard, that's when I first encountered evolutionary theory, and we were taught the classification system, and I didn't really like the way it was being taught, and I always used to hate biology because I thought I always have to just mug up stuff and just regurgitate things when there were exams, when I had to write exams. And I always had an analytical mind, which means like I was decently good with math, and I really liked doing physics, and that's what I did for my undergraduate degree. But somewhere during my undergraduate degree, I kind of lost my interest in physics. I kind of realized this is something that I really liked reading about and working on some tricky problems, but it really didn't fancy me as a research endeavor. And so during that time, I was looking for classes in other departments where I could apply I could do something sort of applied physics. And so the two departments that I kind of narrowed down was ecology and atmospheric sciences. And so one of my we were hanging out, one of my friends came up to me and from biology department, and he told me that, "Oh, Nikunj, you should take this course on theoretical ecology." And I was like, this was the first time I was encountered that you could ever use mathematics in ecology or biology in general. I never thought that was possible, and I was a bit I was like, sure, I would try it out, and I thought like math is something that I can always handle, and I didn't think the biology would be that hard. I was wrong about both the things. Like the biology was very hard, but I was also very surprised the fact that how much math I need to apply to understand ecological and evolutionary systems or biological systems. And so the professor who was teaching that course he himself had a undergraduate degree and a PhD in physics, and then he later on switched to ecology and evolution. And I really liked my time there. This was my undergraduate advisor, Vishwesha Guttal. He's the one who I did my senior thesis with. And so he kind of encouraged me that I should think about doing ecology for my senior thesis. And I had to pull I had to sort of wrestle with the admin in India, because in India the curriculum is very strict, because they wanted me to do a senior project in physics, but somehow I was able to convince them that no, this is mostly physics, but I'm trying to answer questions in ecology and evolution. And eventually I just did my senior thesis in the ecology department. And I was like, at that time was like the 1 year that I did the 1.5 year, 2 years, something of that sort I spent in the ecology and evolution department. And it was like really fascinating. And I learned a lot about ecology. And then my advisor convinced me that I should start thinking about graduate school if I wanted to, and should seriously give a thought about pursuing grad school in ecology and evolution. And so that's how I kind of went on the path of doing biology.
What were the biology courses that you took that required a lot of memorization?
I don't know the title. It was mostly in high school. And so so I think so it was classification system. It was mostly about definitions, like how nutrients get cycled. So the problem was that I think so the way I think about in retrospective now is that I think in a very structured mathematical way. Mathematics is the way I reason about biology. This was a thing that I hadn't discovered about myself. And once I did, I really started enjoying biology.
What I would say about that is that, in my opinion, high school and undergrad biology is a lot of memorization and regurgitation. You have to get a command of a lot of facts before you know how to reason about biology. And if your interest is in analytical reasoning, whether it's advanced mathematics or just thinking about theory or just coming up with ways to test hypotheses, you don't get that a lot in undergrad until you get to a certain stage, like doing senior research or something like that. I would just say that I had the same experiences, even though I am not as mathematically focused as you are. I totally empathize with that perspective.
Yeah, I totally agree. Like, we have to kind of learn the basics about biology. But I think so that there was a particular way the biology was taught in my high school, at least during my school years, that there was like a distinct, there used to be buckets, like math lies in one bucket and biology lies in other bucket. And there is like an absolute separation between them. Like both amongst teachers and who studied those subjects. And I think so that boundary sort of became a bit blur in undergrad, and now that boundary doesn't even exist when I'm at the frontiers of research, because I kind of encounter problems like in biology where mathematicians have to still work on. And similarly, there are many things in mathematics that have been figured out, and then people in biology are going out and testing those predictions, but just based on the theoretical argument. And so that distinction is no longer there, and I'm at least at the forefront for the research, and I'm pretty happy about it. Yeah. So after that, like, I decided to do my master's in ecology and evolution. I spent about 4 years at Yale, and then I came here at UT to work on my PhD with Tim Keitt, who's also a professor at UT Austin. And I joined in 2009, and I've been here for about 2 years now.
Did Tim Keitt and Stephen Stearns ever collaborate or have an interaction?
No. So Steve Stearns was aware of Tim, but some of my committee members and some of the people who I interacted at Yale knew Tim. For instance, there was a professor called David Vassar who knew Tim for a long time, because Tim worked in theory and David Vassar was closely associated with the theoretical ecology section at ESA. So he was actually the person who told me that I should apply to Tim. And in fact, when I was applying to Tim, I later on realized that one of the papers that I was working on, the main theory argument that I was trying to propose or trying to make came from Tim's paper. But that was like, I didn't pay attention to that. It was Tim. And then later on, when I was applying for PhD, I realized, oh, this is the same person.
What is that?
It was about a concept called range pinning. So I was working on, during my master's, I was working on understanding how continental scale boundaries between savannas and forests originate and are maintained over long time scales. And so in Madagascar is a peculiar example where when you observe where the savanna forest boundary is, you kind of see that it is kind of aligned with a dispersal barrier. Like, there is a north to south dispersal barrier along, on the eastern coast of Madagascar. And so basically the Madagascar geography is as follows. On the eastern part of the Madagascar, you have lowland rainforest. And as soon as you go a couple of hundred meters in the island, there is a sudden increase in elevation, and that you enter into the region what we call as Central Highlands. And so what you see is that the savanna forest boundary abruptly stops at this dispersal barrier. And I was trying to explain how this could have maintained the boundary in Madagascar. And so one of the theoretical arguments to explain that concept is through range pinning, and that was proposed by Tim during early 2000s.
What does range pinning mean?
So range pinning is a phenomena that basically arose in the context of invasions. So imagine that you have a species that has a growth rate, has a negative growth rate when there is low abundance, and that could be because of scarcity of mates, and this is what we call as alley effect. And so what happens is whenever you have an alley effect and your dispersal and your dispersal capability is low, then what can happen is that you form a stable range limit even though your growth rate is greater than 0. And it's just basically because of alley effect. In low dispersal limit, the alley effect becomes so strong that you cannot expand even though the climate is favorable for your expansion. And so that is what I was trying to argue in this Madagascar paper, is that even though the climate is so climate was favorable for climate was favorable that could allow rainforest to expand over the central part of the Madagascar, there was this low dispersal region that kind of restricted the savanna forest boundary to the east coast. And so I was trying to explain that pattern using what we call as range pinning.
What do you think is the general role of theory in biology?
General role of theory in biology. Okay, so you asking theory or mathematics?
Maybe both.
Okay, so theory, okay, when I think about theory, I think of theory as more a conceptual construct, of a parsimonious conceptual construct to understand a certain class of patterns. And one way of sort of describing those patterns is through verbal argument. I am of the camp that verbal arguments generally verbal arguments are sometimes get sloppy because you need to be sometimes precise about what you're saying. And that's where mathematics kind of shines out. So mathematics kind of forces you to sort of state what you're saying in a very explicit terms, and then whatever you get at the end is just basically an outcome of what you stated. And so it is a very logical connections between what you stated, which we call as assumptions, and the model output. And so so when I think about theory and ecology and evolution, I think basically it's like the role of theory in biology is same as the role of theory in science. There is no distinction between biology and other sciences. Like people have used theory in physics or like mathematics in physics to make so many really interesting and really important discoveries. And the reason was that because mathematics is very precise, and so it allows you to come up with predictions based on your assumptions, and then you can test your predictions. And similarly in biology too, mathematics allow you to be very precise, and it allows you to come up with analytical predictions or some set of allows you to come up with some set of predictions that can be then tested using either experimentation or observation.
And it can also let you keep track of multiple variables and interactions that might be difficult to keep track of in a verbal argument, right?
Yes. That's the another part. Like I think so the way there's this somebody, like I think so it was Sean Rice's book on evolutionary theory. His argument was that the reason why we do theory is that sometimes we start with what we know, and just by doing mathematics and just following each and every logical step, we come up at a result that we couldn't have known without doing the proper mathematics. And that's the idea, I think. So you're trying to sort of indicate that there's so many things that a verbal argument would miss, that we cannot sort of connect the dots. But mathematics allows us to do that.
You're doing some theoretical modeling, a core foundational approach to spatial sorting. Would you like to first explain the basic conceptual idea behind spatial sorting and then your approach to modeling it?
Yeah, I would love to do that. Okay, so the spatial sorting is like, okay, I should tell why I kind of I started with spatial sorting. So I work on dispersal biogeography, and I'm very interested in trying to understand how ecology and evolution interacts at population margins to determine biogeographical patterns. And so spatial sorting is one of the mechanisms that kind of operate at population margins, by which you can have enhanced dispersal rate. And so to explain what spatial sorting is, I have to talk about first about natural selection. We kind of all, like, I'm assuming whoever is listening to this podcast knows the theory of natural selection, which was proposed by Darwin in 19th century. And one of the key one of the key arguments about Darwin's theory was that you can have, okay, let me rephrase. Darwin and Wallace jointly proposed the theory of natural selection, and the main in which they kind of argue about a biological mechanism by which organisms become adapted to their surroundings. And the three principles, or the three necessary and sufficient conditions for natural selection to operate, is heritability, variation in traits, and differential lifetime reproductive success. And so the argument is that, let's say, if you have a population in which you have variation in a particular trait, let's say your beak length, and that variation is heritable, meaning that you can pass on that variation, or like your beak length is inherited by your offspring in some degree, and having smaller or bigger beak length affect your survival or your reproduction, then over longer time scales, what you will see is the shift in the phenotypic distribution of beak length. And this is what we call as natural selection. And so one of the key requirements of natural selection is differential lifetime reproductive success. That is, some traits leave ancestor with some traits leaves more offspring than others. Okay, so in 2011, there was this paper which was published in PNAS, which talked about an alternate mechanism of selection that does not necessarily require differential lifetime reproductive success. And to sort of intuitively explain this phenomena, let us consider this hypothetical example. So let's say you have a population in which you have variation, and that variation in trait, let's say wing length, and that variation is heritable, meaning that your wing length, the ancestor's wing length is kind of, or the offspring's wing length kind of resembles their parents' wing length. But let's say that having larger wings doesn't really affect anybody's lifetime reproductive success. That is, let's say everybody in that population produces 2 offsprings. Okay, so by that logic, you should not observe natural selection, or you should not you should not observe natural selection. But let's say this population is allowed to expand. So what you would expect is, because wing length facilitates dispersal, then the individuals that are at the population margins will inevitably have longer wing lengths. And when they interbreed amongst themselves, they will again produce offsprings that have longer wing lengths. And these individuals will then occupy or colonize the patches that are in front. And so what you will see over a generation
I've got a question real quick. So when you say the population expand, do you mean just spatially or also numbers?
Spatially.
Okay. So it doesn't need a total increase in numbers.
It can increase in number, but like what in spatial sorting, or this phenomenon which I'm describing is called spatial sorting. In spatial sorting, what you care about is the population margin. So it
doesn't. Spatial sorting does not require a total increase in numbers.
It would be hard to think of an example that would not lead to increase in numbers, because when you're expanding, you're colonizing new areas, and that will increase the total population, like the whole population in the landscape, but it does not necessarily require you to have increased population sizes.
So do you think you could get it though if the total numbers were the same and it just expanded spatially? Maybe that's a question for...
So in life history evolution theory, there is this whole field about how when populations are going to extinction, evolution happens. So evolution, like the way I perceive evolution, is changes in frequency of traits. That frequency.
Well, we can get to the spatial sorting question later, but let's just say for now that the population is expanding in numbers and geographically.
Yeah, let for simplicity, let's say that. And so let's say these populations are expanding, and inevitably the individuals which have longer wing length will accumulate at population margins. And when they locally interbreed with themselves, these longer wing length individuals produce offsprings that are also have longer wing length, because I just stated that this variation in wing length is heritable, and these offsprings are then going to colonize the new patches. And so over successive generations, when you just look at the population margins, you will see is that there is an increase in wing length. The frequency of the mean wing length increases spatially at the margin. And so what you're seeing here is evolution in wing length, even though there is no differential lifetime reproductive success. Instead, what you have is differential dispersal ability. And this mechanism is what Rick Shine and collaborators in their paper called spatial sorting.
Does it depend on sexual reproduction, or would this work with asexual reproduction?
It would work with either kind of section. It's when you say when you say sexual reproduction, you mean diploid organisms.
Sure.
Yeah, it doesn't matter whether it's diploid. And I think so. This is a good segue into how I approach this problem. Okay, so I first encountered this problem in 2016. And I was not an evolutionary biologist, I was an ecologist. And not to say that I didn't know the evolutionary theory, it's just that was not something that I was thinking day in and day out. I was more concerned about understanding population dynamics. But this is something that kind of stayed with me, and I was very interested in understanding how evolution operates at population margins. And I tried creating some simple models of evolution at population margins. And I kind of realized very quickly that in any model that I'm going to make, I have to establish the biological context. And basically, when I say biological context, I mean answering the following three questions. How are the traits inherited? Which traits I'm talking about, and how those traits link to the individual's fitness, or whatever, how linked to the individual's dispersal, or how many offsprings they produce. And the answer to these questions would depend upon the organism I'm talking about. Okay, so for example, if I'm talking about glanville fertility butterflies, which have variation in metabolic rate, there I would be talking about certain genes that kind of regulate the metabolic activity of those butterflies. And many researchers have kind of figured out, particularly Ika Hansky's group have figured out what are the particular genes that regulate the metabolic activity in those butterflies. So if I were thinking about those glanville fertility butterflies, I would be thinking in the context of a diploid model. But let's say if I'm thinking about cane toads, where people have observed that the cane toads, as they are expanding their range, their leg length increases because that facilitates their dispersal. And then I have to think about something like a breeder's model, or Russell Landis and Stephen Arnold's multi-trait phenotypic evolution model, where multiple traits or multiple genes together determine the phenotype, or this is what is called as polygenic trait. And this was kind of unsettling to me, because I thought the idea of spatial sorting was much more general than these assumptions that I had to make. So I was kind of, this was like the physicist in me saying that, okay, we can do something better than this. And so I came across a really good book on evolutionary theory, which was written by Sean Rice. And I think so I should recommend that book to anybody who does evolutionary theory, and in which he kind of takes a different way of building theory. And he says is that the traditional approach in which how we build theory is by we make assumptions about the biological context. And I explained what I mean precisely about that statement. And once we make those assumptions, we are constrained by those assumptions on what we can do. Okay, and so the models that comes from those assumptions apply to that biological context, and those I'll call those special case models. And he says there's another way of building theory in which instead of making assumptions at the start, what you do is you define some unambiguous principles that applies to a large class of biological systems. And the theorems that you derive from those principles then forms the foundational mathematics of selection. And then you can supply assumptions to those mathematical theorems to derive special case models. And when you do that, those special case models are not built in isolation. Instead, they are united under a single conceptual idea. And here it would be the idea of spatial sorting. And so when Sean Rice was writing this book, he argued that this fundamental theorem of natural selection is Price's theorem. And so now I have to kind of talk about who was Price. And George Price was a very fascinating person. Everybody should read about his life. And he was actually a novice. He was somebody from an outside field. He was a chemist. I think so. I might be wrong.
So he worked in information theory, didn't he?
I'm not sure. He worked with Bell Laboratories, I think so. And he also worked on the Manhattan Project.
He did an early CAD machine that didn't take off. He worked in several areas. But...
yeah, he worked in several areas. And one day out of the blue, he writes a letter to Bill Hamilton with what later came out to, describing his work, which later came known to be as the Price equation or Price theorem, in which he outlines the algebra of natural selection. And
he just came at it from a totally outsider's perspective. He didn't have the constraints of preconceived wisdom, right? And he was also at a stage of his life where he was able to think mathematically and just had a wide range of understanding of different areas of science. So he was able to just step into biology and reason, unlike a undergrad student or grad student that had been educated in that field, right? And so,
yes,
just totally new perspective.
A very new perspective. And to give an example of how radical that perspective was, that he showed his work to Richard Lewontin, and who's a very famous evolutionary biologist. And Richard Lewontin had a really hard time understanding what Price had did. And only after years later, he recognized what Price had achieved. And in fact, the contribution of Price went unknown till I would say 1990s, except a few people like Bill Hamilton, who realized the value of Price equation pretty early on. Okay, so what is Price equation? Price equation is it defines the algebra that captures the idea of natural selection, and it does so in a way that it detaches itself from the biology of the system. And this is really hard to explain in a sense. Okay, let me think.
It starts out with just two populations, right?
No, it doesn't even start out with population. It doesn't even start with population. Yeah, it doesn't even start with populations. It starts with something we say as sets. So when you're saying population, you've already assumed that the entities that you're going to talk about are individuals, right? Price doesn't do that. So Price defines something called as an ancestor set and a descendant set. An ancestor set, we intuitively interpret that as parents, and a descendant set, we intuitively interpret that as offsprings. But ancestors and descendants are not necessarily parents and offsprings. They could be parents or grandparents and grandkids too. So that distinction only exists because we are making some assumptions about what we choose to call ancestors and descendants. And so Price equation it's basically an algebraic theorem. It doesn't assume anything about the inheritance mechanism or how traits confer fitness advantage to individuals, and it says that it's going to, if there is a way, let us assume that there is some way in which how these things happen, then this should be the evolutionary change. It is basically trying to re-express evolutionary change in terms of expectations and covariances. And so the neat part about Price theorem was that it allowed us to rediscover much of the evolutionary theory that was established in the 20th century by people like Fisher, Haldane, and Wright. And that was really remarkable because there was another way in which you could rediscover or you could unite various models and evolutionary theory. And later on, people kind of realized that price equation can be used to settle many debates. For example, price equation was very fundamental in understanding Fisher's fundamental theorem of natural selection, which was really difficult for a really long time to understand what Fisher actually meant by his theorem. And later on, Price provided a very crisp and like a very intuitive explanation of what Fisher meant. Then similarly, Price equation was also used to understand multi-level models where you have two levels of biological organization, and selection can operate at both levels of organization. As the famous example for this is altruism. Like altruism, in altruism, there are certain genes that are, the Hamilton divided as what I want to say. Yeah, altruism is one example, or like cancer cells are another example where you have cancer cells that are growing at one level and the organism at one level. And so this idea of using Price's theorem was very fascinating to me. And like I thought maybe I could try using Price's theorem and try to understand how spatial sorting operates. And then I realized that actually Price equation cannot be used to understand spatial sorting because of the way we define evolutionary change. So in Price equation or Price's theorem, we define evolutionary change over a static frame of reference. So the way I think about it is that you're a cameraman and you're observing how things play out in nature, and you point your camera towards a pond or a lake and you observe evolution of fishes over time. Let's say there's a fish that is like, there is a small fish population that is being eaten by a larger fish, and in response to that the smaller fish is evolving. And so as a cameraman, you're looking at the pond and you're observing how trait changes happen in the lake. Okay, when you're thinking about spatial sorting, you're still that cameraman, but now you're running with the population margin such that the population margin is always stationary with respect to you. So both the margin is moving and both the observer is moving, such that they both are stationary with respect to each other. And so this requires a different way of defining evolutionary change, and that is not captured by Price's theorem. So but it was very similar in spirit. And so I used the ideas that were developed by Price, and I derived a theorem of spatial sorting, which I called as the sorting theorem. And what immediately came out from that theorem was that the mathematics of selection was identical for both Price's theorem and the sorting theorem. So what I mean by the mathematics is that the evolutionary change is still defined in terms of covariance and expectations. What changed was fitness. So in the classical natural selection paradigm, what we think of fitness is the number of individuals that you leave at the end of your lifetime, or this is called the lifetime reproductive success. In spatial sorting, what mattered was how many individuals that you leave at the population margin or an empty patch. It doesn't care about how many individuals that you reproduce. It doesn't care about whether you're good and bad at dispersing. What evolution or spatial sorting cares about is how many individuals you leave at the population margin. And the rest, everything is the same.
In your paper, you called it selection, right?
Yes, I call it selection. So
the original paper was drawing a distinction between spatial sorting and selection. So maybe comment on that.
Yeah, I can comment on that. So the original paper kind of, I think so. I should say that that's a remarkable paper. First of all, like it's gotten a lot of us thinking in different ways. So the original paper argued that there are two different ways in which selection operates. One is the traditional way of looking at natural selection. And then there is this spatial sorting. And then they were argued, should we define this as natural selection or not? And they take Rick Shine and collaborators suggest two things. They say that either we can expand the definition of natural selection such that we accommodate spatial sorting, or we could call this as a different phenomena altogether. And so in their paper at the end, they kind of say that we propose to think about this as a separate phenomenon. So it is, I would say it's a semantic choice. Like you could call it you could call it natural selection, or you may not call it natural selection. What matters is that sorting theorem tells us exactly what has to happen for evolution to take place.
I guess I'll just comment on a couple of things. I think there are kind of two general issues that come up with spatial sorting and then your approach to it that I would comment on. The first one is it natural selection or not? And what is the general significance of spatial sorting in evolution overall? So the original paper says that the significance of it is that it leads to the buildup of these dispersal phenotypes on range edges. And then in some cases that could lead to, say, the colonization of an island by the dispersing morph, where it's then kind of limited to that island. And you don't, the spatial sorting would yield a situation where there is a particular place that kind of evolution has produced a new phenotype that's now fixed in that area. So that's one significant aspect of it, is that it could explain some patterns of finding, say, dispersal morphs on islands or similar types of things like that. So from my perspective, and I take a different perspective to what natural selection is compared to the standard textbook definition that you mentioned, which is heritable variation and net reproductive success. Is that the only requirement for something to be selected, right? So if you take that definition, you get into this quagmire, which is, well, species might be able to reproduce by speciation and die with extinction. So it might appear that natural selection ought to apply to the species level. And so then you're wondering, well, might natural selection apply to higher level units than within species? And that was a question that drew a lot of attention from philosophy of biology for a long time. And people argued about what is individuality, what is emergence, what is reproduction, what unit should be considered a unit of selection. And so this problem pestered me for a while. And there was a point in my research where my empirical research endeavors inspired me to just go back and read Darwin with an open mind, dispensing with this assumption that the way he's normally interpreted as making this argument about reproductive success, and just saying, what did Darwin actually say on this issue? And he really started his argument defining the levels of selection with this idea that populations, even slow breeding organisms, would quickly fill the planet if it weren't for various checks to increase. And these checks could be kind of normal resource limitations like food or water, or they could be predators and parasites. And so what follows from that is that two species could be identical in every way and, say, just differ in their parasites and be separate evolving species because they have different checks to increase. And what this means is that the checks to increase are important for defining the levels of selection and what natural selection actually is. And when I looked at the spatial sorting argument, well, let me just say first, that way of reasoning led me to think, okay, the question for extending evolutionary theory is not the levels of selection, but something to do with checks to increase and the fact that periodically throughout the history of life, if life had indeed originated from one or a few forms and Darwin's theory was correct, there must have been transient population increases as life periodically escaped checks to increase, either by, say, innovating ways to find new resources or overcome their predators or parasites. These species would expand in population periodically. And those kind of periodic population increases are kind of overlooked. They're kind of ignored by natural selection because it's not what natural selection is all about. Natural selection is all about within species differences. And so, but of course, the cumulative effect of these population increases over time must be the major trends of evolution. And the question that came in my mind was, is there a different form of competition that's involved with population increases? Does it have different effects? Is there a different non-random force associated with it? And my conclusion was that indeed population increases tend to lead to diversification events. Diversification tends to allow a clade of organisms to be resistant to invasion, yielding a kind of incumbent advantage, which is the reward for innovation. It's the reward for the inventions that allow you to escape checks to increase. And on top of that, complex traits, the kind of evolutionary inventions that lead to expansion, often evolve for reasons that have nothing to do with the causes for why they're expanding. So they evolve, the more complex a trait is, kind of the more likely that it's composed of subtraits. There's important interactions between the subtraits. And therefore, there can be a kind of randomness of invention where some inventions sort of succeed for reasons that have nothing to do with why they originated, a lot like mutation at the level of within species change. And so I called this force natural reward, which kind of non-randomly acts upon invention, which is heritable. And it could also apply to kind of various levels of the genetic hierarchy. And I apply this to explain various things like how we can think about biological progress by analogy to economic progress, like increase of GDP, overall expansion. How do you compare the kind of progressiveness of organisms of different size, where it's not just total population, but biomass or energy flux that might be used as a measure of progress. And then old questions like punctuated equilibrium and what accounts for that phenomenon in the fossil record. And so when I looked at spatial sorting, I saw this is very similar because it's involving an expansion, and it also favors the similar type of traits. In this case, spatial sorting is kind of more focused on traits involved with dispersal, the dissemination. What I'd say is like the dissemination of invention. So like thinking about the cane toad example, like the longer leg is kind of the invention that's being disseminated to new environments. Natural reward, though, over broader timescales would also apply to like evolvability traits. And so the funny thing about it is that I felt like when they came from this perspective that viewed natural selection as heritable variation and reproductive success, and calling spatial sorting something other than natural selection in the sense that it does not require overall population differences in reproductive success, I feel like it's a little bit ignoring what's really important, which is that these traits are often involved with population expansion. I mean, they are often involved with overall increases of population, and that tends to lead to diversification. So what I would say is not natural selection is the population expansion caused by the dispersal traits, right? Like if you got a new trait that allows your population to really expand and get into new environments, and then maybe even speciate because you have so many more organisms, then that's kind of like an innovative trait that can influence these evolutionary trends. You can have this with, it's an interesting phenomenon that is sometimes present in populations and it doesn't lead to big speciation events or major invasions of new resource zones or things like that. So that's my comment on just like the basic framework by which you're approaching spatial sorting. And then the other thing I'd say is just I appreciate the price equation and how it's allowed the unification of models and an understanding of Fisher's theorem. And I think there is a role for mathematics, these kind of general mathematical models in allowing us to kind of understand the basics of selection. There's also a question though of just how do we seek generality in biology in terms of predictive power. And I've just taken a different approach in my research, which I'm not saying it's like one's superior to the other. I'm just saying there's a different approach that I take, which is more the searching for general predictive power by distinguishing the stepwise ways that complex traits evolve independent. Like, so take a trait that's evolved many times independently in different lineages. The one I've been studying is kin recognition. And so it's evolved at unicellular, multicellular, colonial, and also multinucleate levels of biological organization. And at each of those levels, it's evolved many times independently based on different genetic mechanisms and in very different environments and different sorts of organisms. And so I felt like a model if this complex trait evolves for the same reasons or through the same series of events in all these different realms, then by understanding kind of the basic ways it evolves, you can get predictions for a general kind of predictive power. In that case, the basis for prediction comes not from a general mathematical model like Price's equation, but by understanding the sequences of steps that happen over kind of macroevolutionary timescales. And by that, I mean definitely longer than is considered by normal microevolutionary models. So like multiple, like 5 steps of like traits evolving. One leads to the other, leads to the next, leads to the next. And so you kind of understand these basic sequences. And the first model I did on that, it had to make particular assumptions. I mean, I started out kind of like doing a general conceptual model. I talked to a biologist who's very mathematical, Andrew Murray at Harvard, and he just told me that it would be good to have like a case that you could grab a hold of and like understand the biology of it and have the predictions come out of the model and then have the evidence and everything as the first statement of the theory. And that actually was very useful because partly it allowed me to disguise how the basic approach is threatening to some of the current thought in the field, but also just it allowed it kind of minimized the theoretical implications and it maximized the data, the link between theory and data, and that let it be published despite some, I would say, prejudice against the overall approach in the field of social evolution. And so, yeah, those are, I guess I would also say the Price equation in my field, there has been some criticism of it by Van Veelen and a couple of other people. There's a issue of philosophical transactions that came out recently on the Price equation.
And Martin Nowak has also published some criticism about Price equation.
Yeah. So one of his main criticisms just has to do with whether it's useful for predictions in general about particular biological situations. And the way it's been used in the field of social evolution to model Hamilton's rule, from the papers I've read and also just from what I've seen, is in its applications, it's kind of done more harm than good. And I'll explain what I mean by that. Like, Hamilton's rule is a specific statement that depends on particular assumptions and can be used for making predictions about actual biological phenomena. When Dave Queller applied the Price equation approach to the Hamilton's rule, and Nowak and colleagues showed this in a PNAS article, the terms mean very different things than the original equation. They mean like the original equation says that an altruistic behavior, I mean, just in the case of altruism, will be favored if the benefit to the recipient times the relatedness to the actor has to outweigh the cost to the actor of performing the altruism. In that case, the relatedness term is determined by, say, population structure. It can also be determined by discrimination ability. The way Queller did it in the Price equation, the benefit and cost terms also had components of population structure in them. So maybe there's another way to do it based on the Price equation. I don't know. But the Price equation approach was not used to make any particular predictions. I mean, it has not led to any new empirical or theoretical predictions in that case. And what I've also noticed is that it's kind of served this role of propping up this older belief in something called inclusive fitness, which came out of Hamilton's original paper on this topic. And what Hamilton did in that case was modify Wright's maximization formula, from which actually kind of came out of his shifting balance theory, and it was used to refer to like peak climbing on an adaptive landscape, where under his way of looking at it, the peak climbing would just refer to some minor modification, and any major genetic change would come by shifting between peaks. And he actually called his maximization formula Fisher's fundamental theorem. I mean, but Fisher didn't agree with Wright's approach. He didn't agree that it was the same thing. But a lot of people in the field of social evolution say that Hamilton extended Fisher's theorem, and that Fisher's theorem was about maximization. And then when Goel did the general version of Hamilton's rule using the price equation, it became synonymized with inclusive fitness. It's kind of like this holy grail fundamental theorem that they thought could basically predict anything. And so there's this attitude in the field that any general model should be based in terms of the general versions of Hamilton's rule, which itself encapsulates this idea of inclusive fitness maximization. And I think that has created some level of theoretical prejudice against the sort of models that I was doing, where you're taking a different approach, which is instead of trying to find a general theorem and modify it to suit any situation, you look for these processes with more mechanistic models. And in that case, I just use Hamilton's rule the way Hamilton originally used it. And you can get Hamilton's rule from other mathematical frameworks. You can derive it from population genetics or evolutionary game theory or anything like that. So
maybe I can I have a comment about like criticisms of price equation. I think so. The criticism of price equation comes from the uses of price equation, but not price equation itself. And that distinction is very important to make. Price equation is a tautology. It is like saying that 2 equals to 1 plus 1. It is axiomatic, meaning once you define how numbers add up, it's just a way of partitioning things. And like price equation does exactly that. One partitioning is what Price kind of formulated was the natural selection component of it and then the transmission bias of it. Like there were the two components of it. So to call price equation is wrong, I think so is a misnomer. What you could do is that once you start making assumptions, then you can challenge those assumptions. Then you can be like, okay, those assumptions don't make any sense in the biological context. Okay, so then what you're criticizing is the assumptions. You're not criticizing price equation, or that you're criticizing how is one using price equation, but not price equation itself. And when I say price, when you say that Hamilton rule can be derived by different methods, yes, it can be. In fact, large part of evolutionary theory was derived independently of price equation, and that was never the goal. Like it was not that you cannot come up with new evolutionary ideas independently from Price theorem. The idea was that Price theorem allows you to think very structurally, in a very precise manner. It has.
I don't have a problem with the price equation itself. I mean, I don't. It's not like my area of interest or expertise, but I can kind of feel how it's an interesting model, and it could allow you to reason about natural selection in a different way. And I always think that different perspectives can be useful. And I think that my only, exactly like you said, is the way it's used. And in this case, it led to a situation where Hamilton's rule in the general price equation approach was sort of equated to inclusive fitness, which kind of suggests that there's this deep relationship or some kind of dependency between the two concepts. But really, Hamilton's rule is totally independent of the notion of inclusive fitness. Like, you don't have to believe that organisms somehow evolve complex adaptations for the ultimate goal of maximizing inclusive fitness to use Hamilton's rule to explain altruism or to explain the evolution of discriminatory behavior. And I think that the only thing I'm critical of is the way that the price equation was used in that case to kind of try to prop up this older notion about inclusive fitness maximization, which the basic approach of the maximization techniques that Wright was using were going out of style in the field of population genetics precisely when Hamilton imported it into social theory. And the population genetics field as a whole kind of moved towards more historical models of coalescent theory, trying to reconstruct the evolution of traits, like how traits actually evolve, versus looking for these fundamental maximization theorems, which that's a totally different thing than the price equation, the whole maximization question.
Yeah, this is a very good point. Like, I think so coalescent theory provides us a different way of understanding evolutionary change and the evolutionary theory, which is different from like price equation or standard population genetics model.
So what do you think about the relationship between Fisher's theorem informed by the modern understanding that came partly from the price equation versus the more Wrightian maximization approach? Do you think that that there's this, that Fisher's theorem is about maximization like the social evolutionists tend to argue, or is it something different?
So, okay. I was reading Steve Frank's paper, and in there he kind of like, in over multiple papers, he has written about what a price equation can allow us to understand about Fisher's fundamental theorem of natural selection. I think so maximizing fitness happens only in a very specific case, which is first, you don't like, it's when selection is frequency independent. Like, you can derive a simple haploid model and you can write like, if things are growing exponentially and fitness is independent of the frequency of traits, then the evolution would happen in such a way that the fitness increases over multiple generation. But what could happen is that your environment could deteriorate, because like, let's say if you have more population, more number of individuals, then you have limited number of resources. And and if that is somehow frequency dependent, then you don't have this maximization fitness kind of a thing.
It also seems to me it's about not just say frequency dependence, but also complex genetic interactions, because Fisher, like what Frank talked about in those papers, Fisher's theorem and the kind of generality of Fisher's theorem works because it's talking about a brief moment in time. It's talking about the additive genetic variance of population at one moment in time. It's not talking about predicting some future state of the population. So if you're going to try to get to that future state of the population, then all those complex genetic interactions come more into play of determining the course of change. And I think that's what, I mean, so the way Wright used the equation, he was using it in this particular context of thinking about just a very minor change, because the peak climbing on his adaptive landscape is not talking as the adaptive landscape is sometimes pictured, where you have different species, say, on different hills, where it's like all the complex traits of the species are being optimized to the final goal of like meeting this niche. It was more like each peak was a population within a deme within the species, and the demes differed in their complex genetic underpinning, and they just between within a peak, within that mountain, like there's not much genetic variation in terms of genetic interactions. It's just like a small difference. Climbing the hill is just like, say, a simple quantitative trait or something like that. Anyway, so where are you going to go after this paper? Are you going to keep going down this road? Are you going to try to derive more particular models for particular situations? Are you going to use it for any kind of predictions?
Yeah. So that's something that I've been thinking about. And so one thing that I kind of want to start back at questions that I kind of really wanted to answer when I started thinking about this topic itself. So I have proposed like a couple of quantitative genetics models of natural selection based on the sorting theorem. And they kind of allow us to measure the rate of evolutionary change. Okay, so why do we care about rate of evolution of dispersal? So for example, in a metapopulation, so we know like Richard Levins, the guy who proposed the metapopulation theory of metapopulation theory, in which he outlined that the patch occupancy, or the number of proportion of the patches, or the stability of a metapopulation, is determined by the colonization and extinction probability in a patch. So let's say there's a metapopulation out of and there's a probability that each patch will go extinct, and there's a colonization probability that depends upon the species. Then there is some equilibrium number of patches that will be occupied after some point of time. And we know that as the climate is changing and as human pressure is increasing on our terrestrial biomes, the extinction rate is increasing, right? And so what that means is that we are increasing the risk of extinction. One way by which organisms can mitigate the risk of extinction is by increasing the colonization rate, or in an evolutionary sense, by evolving to have higher colonization rate. And that is something that we have observed in many systems. One of the classical systems is this western bluebirds. So western bluebirds are found in Montana, where what happens is that what you see is that the birds that colonize new patches tend to be more aggressive, and this aggressiveness is sort of genetically integrated with their dispersal ability. So an obvious question that you might ask is, what is the rate of evolution? Because if traits related to dispersal can evolve fast, then those populations can buffer against extreme weather events or extreme climatic events. And so I'm collaborating with this researcher named René Duckworth, who has been collecting phenotypic distribution data on western bluebirds in Montana for the last 15 years. And so from her data, I want to measure selection gradients. Okay, but now the idea is, why is sorting theorem important to measure selection gradients, right? So in the theory of natural selection, the selection gradient or standardized selection gradient, we obtain standardized selection gradients by regressing relative sorting fitness with standardized trait values or standard of parent trait values, and the slope of that line gives us the selection gradient. And so now the question is, what would be selection gradient in the context of spatial sorting? And from the sorting theorem, I can show it's the relative sorting fitness regressed as a function of mid-parent value. And so these definitions, these evolutionary meaningful definitions, automatically emerge from Price theorem. So that is one of the places where I want to apply the Price theorem, or not the Price theorem, but the model that comes from Price theorem. Sorry, the model that comes from sorting theorem.
Okay. What do you think about if organisms are able to respond to climate change by shifting their habitat ranges? What are the implications of that for adaptation? And what I mean by that is, our understanding of that, the approach evolutionists often take to adaptation is, you see an organism in nature in its habitat, it looks adapted, perfectly fit to its environment and its surroundings. And then the assumption often is that the organism evolved in order to meet that habitat requirement by natural selection. Like natural selection gradually fashioned the organism to meet that environmental demand. Well, let me just say that does lead sometimes to some dilemmas, like Haldane's dilemma, which has been beaten to death, and there's various ways of looking at it. But one of the fundamental problems is just sometimes the speed of adaptation is slow, or slower than the environment is changing. And so then you would expect that the species goes extinct. And I've thought that this dilemma comes partially from not allowing for, when we look at adaptation, the effects of organisms shifting their ranges or moving into places where they're able to live, thus avoiding extinction that would be predicted by Haldane's dilemma, right? Just that evolution can't proceed that fast. And but it also means that some adaptation, especially if an organism, maybe through spatial sorting or getting into new places where its traits match a new environment, it might have a new interaction with the environment. And that interaction comes from whatever traits it had previously that had a different relationship to its environment, now having a new relationship to the new environment. Sometimes that new relationship is improved and it's very different. And when we look at it in hindsight, we assume that the organism evolved to meet that environmental condition by natural selection, even though some of the fit between organism and environment is determined by the shifting of the ranges. I think it's just one of the ways out of like a Haldane's dilemma type of situation. But I mean,
yeah, no, this is a very interesting thing to think about. Yeah, so one way of thinking about climate change and adaptation is that like there are only three possible things that a species can do when things change, like whether it can climate or it's anything, something else. It's like either it can adapt, it can move, or it can go extinct. Okay, these are the only possibilities, right? Like, and so when we think about adaptation, like we thinking about closed populations. I think so that's what we kind of are changing our view about. We're thinking about that you can adapt, simultaneously expand, right? And this is what a lot of people are now suggesting in the field, that evolution of dispersal can allow you to better track your climatic niches. So you have this climatic envelope that is moving towards the poles as Earth is becoming hotter. And if the climate velocity exceeds the species velocity, then the organisms may not have enough time to adapt to the newer climatic conditions, and they might go extinct. What can simultaneously happen is that you can evolve dispersal, and then by that you can increase your species velocity, and you can better track the climatic envelope, and by that you always remain in a climatic sphere or an envelope where you have a positive growth rate, if that makes sense. But it's like a double-edged sword. Like what could also happen is spatial sorting could drive evolution in a direction that is maladaptive. And that is, we kind of know this from many places. For example, in cane toad example, so as the cane toads were expanding, their leg length was increasing, but so was their body size. And because of increase in their body size, their parasite load increased, and that increased their mortality. So it's like spatial sorting is a double-edged sword. Like, and
I think they also had some kind of spinal issues too with the longer legs.
It could be, yes. I didn't read that paper, but I definitely encountered a paper where increase in leg size led to increase in body size, that led to increase in parasite load. And there are several examples even in in some Ageria butterflies in UK, where it was observed that butterflies at the margins had larger thorax than their cores, which was an indication of spatial sorting happening. But that also meant that they also left fewer number of eggs as compared to the core population. So their reproductive output was decreasing. So this, both spatial sorting and natural selection kind of leads to these interesting combination of trait evolution. And
so I do like kind of separating spatial sorting from selection, conceptually as they did it in the first article, partly because I think there's also something that might be called temporal sorting, which, hold on for a second, because I know that sounds to be natural selection, right? But there are organisms that produce, let's say, hardy resting stages, especially some microbes, and they do this thing called phenotype switching, where they'll produce a genetically identical morph which has a totally different phenotype. And they do this every several thousand cell divisions. And then every several thousand cell divisions, they switch back. When the environment is normal, you just have the normal phenotype having the highest reproductive success. And that's all you see. But these hardy resting stages are continually produced at a low frequency, and you barely see them. And then if there's a disaster, they are still there, along with the exact genotype that was there in the normal environmental conditions. And then they can go through a disaster situation indefinitely in that hardy stage, which does reproduce, but usually more slowly. And then as soon as the conditions become favorable again, or almost as soon, because it happens every several thousand cell divisions, then all of a sudden you have the normal type again. It seems to me that that's almost like a spatial sorting through time. It might not be favored by natural selection. It might be, it could be possibly, depending on the organism, but it definitely would be favored in the longer term of evolution.
seems to me more like bet hedging. Like bet hedging, exactly. It's almost exactly like this.
Yeah, there are
thing.
models of bet hedging, and they're also there. You can do a selective model of it, but I'm just saying that in the longer that it can also be favored by expansion, which, as I'm saying, is not usually captured by. So if you imagine a situation, for example, where the entire world is decimated, the things that do that sort of thing are going to repopulate the world, or just big resource zones. The hardy ones can live through these kind of black swan type of events, and that's not captured by a typical bet hedging model of selection over intermediate timescales. But it might be something that
I would think it would be a part of natural selection. So like, okay, entertain me for a second. So let's say you have periodic disturbances and they wipe out most of the population except that phenotype. Okay. So now I say is, let's say there is some frequency at which a particular, what do you say? These disturbances happen. Okay. So let's say there is a genotype in which you do not have the hardy phenotype and in which you have a hardy phenotype. After 1 million years, which of the phenotypes will survive? The hardy one. Because the other one would get wiped up by the disturbance.
Yeah, I just, especially if it's allowing, I would just say that if it's allowing you to colonize new environments and expand and speciate, then it's something different than natural selection. If you're talking about being preserved within a population, then that's more of a selective type of model. And I would say the same thing for spatial sorting. Like, as soon as, for me, the main difference isn't that the thing that distinguishes spatial sorting from natural selection is not that it doesn't involve a population-wide difference in reproductive success. I understand that argument. I can see how that differs from one concept of natural selection, but to me, the important one is just that it lets you get in. It lets the population expand, and as soon as you get into that to me, as soon as you start to get into expansions, is where you're talking about something, expansion, possible speciation. That's when you're getting into a different realm. That's kind of the meeting point between typical evolutionary theory and ecology. But over a broader timescale, would be a meeting point between kind of more microevolution and macroevolution type of processes. But it's just kind of a minor point. But I think there is a parallel between the way spatial sorting can let you get into new environments and expand, and the way some traits involved with dispersal through time, through these events that might happen periodically with destructive effects, would allow colonization of new habitats. But I noticed in your paper you cited Darwin and Wallace instead of Darwin.
Yeah, I did that on purpose.
I think that early paper was the better paper was Wallace's paper, because the first set of papers, it was just a few notes of Darwin, I think a letter, and the paper was Wallace's paper. And I do think that there's some things overlooked sometimes when people cite Wallace, like that he didn't use the metaphor of natural selection.
Yes, he did. Yes.
And I think a lot of people say Wallace discovered natural selection. And I think that natural selection, I don't think you can say somebody discovered natural selection unless they actually talked about that metaphor, because to me, the metaphor was this really powerful metaphor that Darwin came up with and really developed in the first chapter of his book by making the analogy to artificial selection. And that allowed him to really give a foreshadowing of his whole theory in his first chapter, basically going through all the ways natural selection can work in an example that everybody already accepted, which was artificial selection. And that's like a really inventive and creative way to convince an audience with a rhetorical argument at a time when that was the most important thing to getting people on board with it, was figuring out a way to communicate this new idea to people.
I think, yeah, I think there is no denying that Darwin wrote a masterpiece. Like he kind of tapped into very today we would call Darwin as a polymath, because he used so many different lines of evidence to argue about the process of natural selection. But I felt when I was putting that citation, like earlier I had the citation of like origin of species, but then I kind of reasoned about that the crux of the idea was still there even in Wallace's argument. He was not very articulate as Darwin, but rarely anybody is. Like if Darwin is the bar, then it's very high. So in that respect, I kind of credited, not credited, but I thought it makes sense to sort of talk about natural selection as something which Wallace and Darwin jointly proposed. Let's say if I was talking about phylogeny, then I would just cite Darwin. Like the idea of phylogeny originated in Origin of Species. That was the only figure that is there. But the idea of natural selection, if you're not picky about the word and the framing, I would say it was jointly proposed by Wallace and Darwin.
I tend to give credit to Wallace, not with the idea of natural selection, but in very fully understanding the logical basis of it, and then also in some ways expressing the limitations of it better than Darwin did. In the Origin, Darwin does waffle between the question of whether natural selection produces only kind of relative perfection to the immediate environment, or whether there's kind of like absolute perfection, or whether there's an overall progress where newer species tend to be somehow superior and beat their predecessors, and the older species being inferior. And in one of his works, Wallace said that natural selection has no power to produce absolute perfection, only relative perfection, and that it only allows an organism to beat its nearest competitors under the struggle for existence. And of course, Wallace then went on these tangents about, like the people at the time, he was still somewhat spiritual, and he saw mankind differently and thought there might be some other things involved. But he did talk about, I think he was one of the first people to talk about pre-adaptation, of the problem posed by the fact that some traits exist that are very complex, that allow an interaction with the environment, but they're not kind of immediately favored for that reason, or they wouldn't be explained by natural selection for whatever reason they're ultimately serving. And he talked a lot about the traits of humans in that article, but I think it kind of drew attention to the problem of like how a trait appears to us at the present time in its full complexity of design versus to the problem that a lot of the subtraits of a complex trait wouldn't be favored conceivably for the ultimate purpose. Like they all have to come together. So it doesn't necessarily mean that a divinity like planned it, right? That was his like alternative explanation. What it could mean is that natural selection in those earlier moments in time was doing something different, and then it only like happened to come together at the end. I think he said something like, well, it doesn't have to be God. It could be like an archangel. You know? But
I haven't read those texts.
Yeah, I'm just a nut for history of evolutionary biology.
Yeah,
right.
I only really started focusing on evolutionary theory like only a year ago. So
you got an award for your paper, right? On the Madagascar stuff.
Yes,
ecology.
We did.
The Ecological Society.
Yes,
and that was what you were talking about earlier with.
Yeah. That was
the range spinning.
I was talking. Yeah, exactly.
Nice. Well, Nikunj, it was a pleasure. Thanks for being on the Natural Reward podcast.
Yeah,
and,
I had fun chatting with you.
Maybe we'll meet for some future discussion. Thank you.
Sure.
Okay.
Cool.
For more information, go to naturalreward.com, where you can leave comments and find links and references. I'm your host, Owen Gilbert. Thank you for listening.